Coastal management is defense against flooding and erosion and techniques that allow erosion to claim land. Historical background: coastal engineering, as it relates to harbors, starts with the development of ancient civilizations together with the origin of maritime traffic, perhaps before 3500 BC. Docks, breakwaters, and other harbor works were built by hand and often in a grand scale. Basic source of modern literature on coastal engineering is the European Code of Conduct for Coastal Zones issued by the European Council in 1999. This document was prepared by the group of specialists on coastal protection and should be used as a source of inspiration for national legislation and practice by decision-makers. The group of specialists set up in 1995, pursuant to a decision by the Committee of Ministers of the Council of Europe, met for the first time on 6 and 7 June 1996. It noted that a great deal of technical and scientific research had been carried out in the field of coastal protection and that various principles and legal texts had been drawn up. It also noted that all of the work undertaken highlighted the need for integrated management and planning of coastal areas, but that, despite all the efforts already made, the situation of coastal areas continued to deteriorate. The group had acknowledged that this was due to difficulties in implementing the concept of integrated management, and that it was becoming necessary to provide instruments which would make it easier to apply the principles of integrated coastal management and planning, which had to be pursued to ensure sustainable management of coastal areas. The group therefore proposed that the Council of Europe, in close cooperation with the Coastal and Marine Union and United Nations Environment Programme, the final version of the code as well of the model LAW to be used as a guide for modifying local and national legislation, can be free downloaded from the web. Ancient harbour works are still visible in a few of the harbours that exist today, while others have recently been explored by underwater archaeologists. Most of the grander ancient harbour works have disappeared following the fall of the Roman Empire. Most coastal efforts were directed to port structures, with the exception of a few places where life depended on coastline protection. Venice and its lagoon is one such case. Protection of the shore in Italy, England and the Netherlands can be traced back at least to the 6th century. The ancients understood such phenomena as the Mediterranean currents and wind patterns and the wind-wave cause-effect link. The Romans introduced many revolutionary innovations in harbour design. They learned to build walls underwater and managed to construct solid breakwaters to protect fully exposed harbours. In some cases wave reflection may have been used to prevent silting. They also used low, water surface breakwaters to trip the waves before they reached the main breakwater. They became the first dredgers in the Netherlands to maintain the harbour at Velsen. Silting problems here were solved when the previously sealed solid piers were replaced with new open-piled jetties. Middle Ages, the threat of attack from the sea caused many coastal towns and their harbours to be abandoned. Other harbours were lost due to natural causes such as rapid silting, shoreline advance or retreat, etc. The Venetian lagoon was one of the few populated coastal areas with continuous prosperity and development where written reports document the evolution of coastal protection works. Engineering and scientific skills remained alive in the East, in Byzantium, where the Eastern Roman Empire survived for 600 years while Western Rome decayed. Modern age: although great strides were made in the general scientific arena, little improvement was done beyond the Roman approach to harbour construction after the Renaissance. In the early 19th century, the advent of the steam engine, the search for new lands and trade routes, the expansion of the British Empire through her colonies, and other influences, all contributed to the revitalization of sea trade and a renewed interest in port works. 20th century, evolution of shore protection and the shift from structures to beach nourishment. Prior to the 1950s, the general practice was to use hard structures to protect against beach erosion or storm damages. These structures were usually coastal armouring such as sea walls and revetments or sand-trapping structures such as groins. During the 1920s and 30s, private or local community interests protected many areas of the shore using these techniques in a rather ad hoc manner. In certain resort areas, structures had proliferated to such an extent that the protection actually impeded the recreational use of the beaches. Erosion of the sand continued, but the fixed back beach line remained, resulting in a loss of beach area. The obtrusiveness and cost of these structures led in the late 1940s and early 1950s to move toward a new, more dynamic method. Projects no longer relied solely on hard coastal defense structures, as techniques were developed which replicated the protective characteristics of natural beach and dune systems. The resultant use of artificial beaches and stabilized dunes as an engineering approach was an economically viable and more environmentally friendly means for dissipating wave energy and protecting coastal developments. Over the past 100 years, the limited knowledge of coastal sediment transport processes at the local authorities level has often resulted in inappropriate measures of coastal erosion mitigation. In many cases, measures may have solved coastal erosion locally but have exacerbated coastal erosion problems at other locations up to tens of kilometers away or have generated other environmental problems. Current challenges in coastal management. The coastal zone is a dynamic equilibrium area of natural change and of increasing human use. They occupy less than 15% of the Earth's land surface, yet accommodate more than 40% of the world population. With 3/4 of the world population expected to reside in the coastal zone by 2025, human activities originating from this small land area will impose an inordinate amount of pressures on the global system. Coastal zones contain rich resources to produce goods and services and are home to most commercial and industrial activities. In the European Union, almost half of the population now lives within 50 kilometers of the sea, and coastal zone resources produce much of the Union's economic wealth. The fishing, shipping and tourism industries all compete for vital space along Europe's estimated 89,000 kilometers of coastline, and coastal zones contain some of Europe's most fragile and valuable natural habitats. Shore protection consists up to the 50s of interposing a static structure between the sea and the land to prevent erosion and/or flooding, and it has a long history. From that period, new technical or friendly policies have been developed to preserve the environment when possible. It is already important where there are extensive low-lying areas that require protection. For instance, Venice, New Orleans, Negra River in Japan, the Netherlands, Caspian Sea. Protection against sea level rise in the 21st century will be especially important, as sea level rise is currently accelerating. This will be a challenge to coastal management, since sea walls and breakwaters are generally expensive to construct, and the costs to build protection in the face of sea level rise would be enormous. Changes in sea level have a direct adaptative response from beaches and coastal systems, as we can see in the succession of a lowering sea level. When the sea level rises, coastal sediments are in part pushed up by wave and tide energy, so sea level rise processes have a component of sediment transport landwards. This results in a dynamic model of rise effects with a continuous sediment displacement that is not compatible with static models where coastline change is only based on topographic data. Planning approaches for Oscar Beamish. There are 5 generic strategies. 1. For coastal defense. Inaction leading to eventual abandonment, managed retreat or realignment, which plans for retreat and adopts engineering solutions that recognize natural processes of adjustment, and identifies a new line of defense where to construct new defenses. Hold the line. Shoreline protection, whereby sea walls are constructed around the coastlines. Move seawards. This happens by constructing new defenses seaward the original ones. Limited intervention, accommodation, by which adjustments are made to be able to cope with inundation, raising coastal land and buildings vertically. The decision to choose a strategy is site-specific, depending on pattern of relative sea level change, geomorphological setting, sediment availability and erosion, as well as series of social, economic and political factors. Alternatively, integrated coastal zone management approaches may be used to prevent development in erosion or flood-prone areas to begin with. Growth management can be a challenge for coastal local authorities who often struggle to provide the infrastructure required by new residents seeking sea-change lifestyles. Sustainable transport investment to reduce the average footprint of coastal visitors is often a good way out of coastal gridlock. Examples include Longton and the Gold Coast Oceanway. The managed retreat option, involving no protection, is cheap and expedient. The coast takes care of itself and coastal facilities are abandoned to coastal erosion, with either gradual landward retreat or evacuation and resettlement elsewhere. This is the usual response when land of little value will be lost. The only pollution produced is from the resettlement process. Where endangered property has high value, it is less often applied. Managed retreat. Managed retreat is an alternative to constructing or maintaining coastal structures. Managed retreat allows an area to become flooded. This process is usually in low-lying estuarine or deltaic areas and floods land that has at some point in the past been reclaimed from the sea. Managed retreat is often a response to a change in sediment budget or to sea level rise. The technique is used when the land adjacent to the sea is low in value. A decision is made to allow the land to erode and flood, creating new shoreline habitats. This process may continue over many years and natural stabilization will occur. The earliest managed retreat in the UK was an area of 0.8 ha at Northey Island in Starfish Island flooded in 1991. This was followed by Tollesbury and Orplands in Essex, where the sea walls were breached in 1995. In the Bro Delta coastal authorities have planned a managed retreat in response to coastal erosion. Cost €. The main cost is generally the purchase of land to be flooded. Compensation for relocation of residents may be needed. Any other human-made structure which will be engulfed by the sea may need to be safely dismantled to prevent sea pollution. In some cases, a retaining wall or bund must be constructed inland in order to protect land beyond the area to be flooded, although such structures can generally be lower than would be needed on the existing coast. Monitoring of the evolution of the flooded area is another cost. Costs may be lowest if existing defences are left to fail naturally, but often the realignment project will be more actively managed, for example by creating an artificial breach in existing defences to allow the sea in at a particular place in a controlled fashion, or by preforming drainage channels for created salt marsh. Hold the line. Human strategies on the coast have been heavily based on a static engineered response, whereas the coast is in, or strives towards, a dynamic equilibrium. Solid coastal structures are built and persist because they protect expensive properties or infrastructures, but they often relocate the problem downdrift or to another part of the coast. Soft options like beach nourishment, while also being temporary and needing regular replenishment, appear more acceptable, and go some way to restore the natural dynamism of the shoreline. However, in many cases there is a legacy of decisions that were made in the past which have given rise to the present threats to coastal infrastructure and which necessitate immediate shore protection. For instance, the sea wall and promenade of many coastal cities in Europe represents a highly engineered use of prime seafront space, which might be preferably designated as public open space, parkland and amenities if it were available today. Such open space might also allow greater flexibility in terms of future land use change, for instance through managed retreat, in the face of threats of erosion or inundation as a result of sea level rise. Forest dunes areas represent a natural reserve which can be called upon in the face of extreme events. Building on these areas leaves little option but to undertake costly protective measures when extreme events threaten. Managed retreat can comprise setbacks, rolling easements and other planning tools including building within a particular design life. Maintenance of those structures or soft techniques can arrive at a critical point to change adopted strategy. Structural or hard engineering techniques, that is using permanent concrete and rock constructions to fix the coastline and protect the assets located behind. These techniques, sea walls, groins, detached breakwaters, and revetments represent a significant share of protected shoreline in Europe. Soft engineering techniques, building with natural processes and relying on natural elements such as sands, dunes and vegetation to prevent erosive forces from reaching the backshore. These techniques include beach nourishment and sand dunes stabilization. Move seaward, the futility of trying to predict future scenarios where there is a large human influence is apparent. Even future climate is to a certain extent a function of what humans choose to make of it, for example by restricting greenhouse gas emissions to control climate change. In some cases, where new areas are needed for new economic or ecological development, a move seaward strategy can be adopted. Examples from erosion include Code Bay Western Scheldt Estuary, Sheikh Leyland, Bro Delta. There is an obvious downside to this strategy. Coastal erosion is already widespread, and there are many coasts where exceptional high tides or storm surges result in encroachment on the shore, impinging on human activity. If the sea rises, many coasts that are developed with infrastructure along or close to the shoreline will be unable to accommodate erosion. They will experience a so-called coastal squeeze, whereby the ecological or geomorphological zones that would normally retreat landwards encounter solid structures and are squeezed out. Wetlands, salt marshes, mangroves and adjacent freshwater wetlands are particularly likely to suffer from this squeeze. An upside to the strategy is that moving seaward can create land of high value which can bring the investment required to cope with climate change. Limited intervention. Limited intervention is an action taken whereby the management only solves the problem to some extent, usually in areas of low economic significance. Measures taken using limited intervention often encourage the succession of halosiers, including salt marshes and sand dunes. This will normally result in the land behind the halosier being more sufficiently protected, as wave energy will be dissipated by the accumulated sediment and additional vegetation residing in the newly formed habitat. Although the new halosier is not strictly man-made, as many natural processes will contribute to the succession of the halosier, anthropogenic factors are partially responsible for the formation as an initial factor was needed to help start the process of succession. This must not be confused with accommodate, which is about property, for example effective insurance, early warning systems, and not about habitat. Construction techniques. The following is a catalogue of relevant techniques that could be employed as coastal management techniques. The costs given are very rough estimates made during 2005, based on UK pound sterling. Hard engineering methods. Groins. Groins are barriers or walls perpendicular to the sea, often made of green hearts, concrete, rock or wood. Beach material builds up on the down drift side, where littoral drift is predominantly in one direction, creating a wider and a more plentiful beach, therefore enhancing the protection for the coast because the sand material filters and absorbs the wave energy. However, there is a corresponding loss of beach material on the updrift side, requiring that another groin to be built there. Moreover, groins do not protect the beach against storm-driven waves, and if placed too close together will create currents, which will carry sand material offshore. Groins are extremely cost-effective coastal defense measures, requiring little maintenance, and are one of the most common coastal defense structures. However, groins are increasingly viewed as detrimental to the aesthetics of the coastline, and face strong opposition in many coastal communities. Many experts consider groins to be a soft solution to coastal erosion because of the enhancement of the existing beach. But groin construction creates a problem known as terminal groin syndrome. The terminal groin prevents longshore drift from bringing material to other nearby places. This is a common problem along the Hampshire and Sussex coastline in the UK. An example is Worthing. Beach material does not get washed away because of these groins but can cause damage to other parts of the coast. Sea walls. Walls of concrete or rock, built at the base of a cliff or at the back of a beach, are used to protect a settlement against erosion or flooding. They are usually about 3–5 meters high. Older-style vertical sea walls reflected all the energy of the waves back out to sea, and for this purpose were often given recurved crest walls which also increase the local turbulence, and thus increasing entrainment of sand and sediment. During storms, sea walls help longshore drift. Modern sea walls aim to redirect most of the incident energy, resulting in low reflected waves and much reduced turbulence, and thus take the form of sloping revetments. Current designs use porous designs of rock, concrete armour with intermediate flights of steps for beach access, whilst in places where high rates of pedestrian access are required, the steps take over the whole of the frontage, but at a flatter slope if the same crest levels are to be achieved. Care needs to be taken in the location of a seawall, particularly in relation to the swept prism of the beach profile, the consequences of long-term beach recession and amenity crest level. These factors must be considered in assessing the cost-benefit ratio, which must be favorable in order to justify construction of a seawall. Seawalls can cause beaches to dissipate, rendering them useless for beachgoers. Their presence also scars the very landscapes that they are trying to save. Modern examples can be found at Cronulla, Blackpool, Lincolnshire and Wallasey. The sites at Blackpool and Cronulla can be visited both by Google Earth and by local webcams. An example is the seawall at Sandwich, Kent, where the Seaby seawall is buried at the back of the beach under the shingle with crest level at road curb level. Seawalls are probably the second most traditional method used in coastal management. Seawalls cost £10,000 per metre, £10 million per km. Revetments. Wooden slanted or upright blockades, built parallel to the sea on the coast, usually towards the back of the beach to protect the cliff or settlement beyond. The most basic revetments consist of timber slants with a possible rock infill. Waves break against the revetments, which dissipate and absorb the energy. The cliff base is protected by the beach material held behind the barriers, as the revetments trap some of the material. They may be watertight, covering the slope completely, or porous, to allow water to filter through after the wave energy has been dissipated. Most revetments do not significantly interfere with transport of longshore drift. Since the wall greatly absorbs the energy instead of reflecting, it erodes and destroys the revetment structure. Therefore, major maintenance will be needed within a moderate time of being built. This will be greatly determined by the material the structure was built with and the quality of the product. The cost €1 confirmed by material used is $2,340 €, $4,000. Average $10 per metre built €, around £6 GBP. Rock armour. Also known as riprap, rock armour are large rocks piled or placed at the foot of dunes or cliffs with native stones of the beach. This is generally used in areas prone to erosion to absorb the wave energy and hold beach material. Although effective, this solution is unpopular due to the fact that it is unsightly. Also, longshore drift is not hindered. Rock armour has a limited lifespan, it is not effective in storm conditions, and it reduces the recreational value of a beach. The cost is around £3,000 per metre, depending on the type of rocks used. Gabions. Boulders and rocks are wired into mesh cages and usually placed in front of areas vulnerable to heavy erosion, sometimes at cliff's edges or jag out at a right angle to the beach like a large groin. When the seawater breaks on the gabion, the water drains through leaving sediments, also the rocks and boulders absorb a moderate amount of the wave energy. Gabions need to be securely tied to prevent abrasion of wire by rocks, or detachment of plastic coating by stretching. Hexagonal mesh distributes overloads better than rectangular mesh. Downsides include wear rates and visual intrusiveness. Cost €. £11 per m, offshore breakwater. Enormous concrete blocks and natural boulders are sunk offshore to alter wave direction and to filter the energy of waves and tides. The waves break further offshore and therefore reduce their erosive power. This leads to wider beaches, which absorb the reduced wave energy, protecting cliff and settlements behind. The dolos, which was invented by a South African engineer in East London, has replaced the use of enormous concrete blocks because the dolos is much more resistant to wave action and requires less concrete to produce a superior result. Similar concrete objects like the dolos are the Ajax, Acman, XBLOC and the tetrapod, acropode. See also artificial reef. Cost €. £2,000 per m. Water depth may increase the cost. Cliff stabilization. Cliff stabilization can be accomplished through drainage of excess rainwater through terracing, planting, and wiring to hold cliffs in place. Cliff drainage is used to hold a cliff together using plants, fences and terracing. This is used to help prevent landslides and other localized damage. Entrance training walls. Rock or concrete walls built to constrain a river or creek discharging across a sandy coastline. The walls help to stabilize and deepen the channel, which benefits navigation, flood management, river erosion and water quality, but can cause coastal erosion due to the interruption of longshore drift. One solution is the installation of a sand bypassing system to pump sand under and around the entrance training walls. Cost €1 expensive. A Gold Coast Seaway was a $50 million Australian project in the 1980s, and the adjacent sand bypassing project costs $3 million Australian per year to pump 500,000 cubic meters of sand across the trained entrance. Floodgates. Storm surge barriers, or floodgates, were introduced after the North Sea flood of 1953 and are a prophylactic method to prevent damage from storm surges or any other type of natural disaster that could harm the area they protect. They are habitually open and allow free passage, but close when the land is under threat of a storm surge. The Thames Barrier is an example of such a structure. Soft engineering methods, beach replenishment. Beach replenishment or nourishment is one of the most popular soft engineering techniques of coastal defense management schemes. This involves importing sand off the beach and piling it on top of the existing sand. The imported sand must be of a similar quality to the existing beach materials so it can integrate with the natural processes occurring there, without causing any adverse effects. Beach nourishment can be used alongside the groin schemes. The scheme requires constant maintenance, 1 to 10-year life before first major recharge. Cost €. A £5,000 or £200,000 per 100 metre, plus control structures, ongoing management and minor works. Sand dune stabilisation. Vegetation can be used to encourage dune growth by trapping and stabilising blown sand. Cost €. of a £1.1 million per annum. Beach drainage. Beach drainage or beach face dewatering lowers the water table locally beneath the beach face. This causes accretion of sand above the drainage system. 2. Grant €. The elevation of the beach water table had an important bearing on deposition and erosion across the foreshore. A high water table coincided with periods of accelerated beach erosion, and conversely, a low water table coincided with pronounced degradation of the foreshore. A lower water table facilitates deposition by reducing flow velocities during backwash and prolonging laminar flow. In contrast, a high water table results in condition favoring beach erosion. With the beach in a saturated state, Grant proposed that backwash velocity is accelerated by the addition of groundwater seepage out of the beach within the effluent zone. Turner and Letherman, moving from the origins and development of the dewatering concept to field and laboratory studies available at the time of writing, concluded that there was too little evidence for being convinced that the systems had a positive effect. None of the case studies provide full scientific evidence of indisputable positive results regarding beach stabilization, although in some cases an overall positive performance was reported. In many cases no adequate long-term monitoring was undertaken at a frequency high enough to discriminate the response to high-energy erosive events. A useful side effect of the system is that the collected seawater is very pure because of the sand filtration effect. It may be discharged back to sea but can also be used to oxygenate stagnant inland lagoons/marinas or used as feed for heat pumps, desalination plants, land-based aquaculture, aquariums or seawater swimming pools. Beach drainage systems have been installed in many locations around the world to halt and reverse erosion trends in sand beaches. 24 beach drainage systems have been installed since 1981 in Denmark, USA, UK, Japan, Spain, Sweden, France, Italy and Malaysia. Costs. The costs of installation and operation per meter of shoreline protection will vary due to system length, pump flow rates, soil conditions, discharge arrangement/filtered seawater utilization, drainage design, materials selection and installation methods, geographical considerations, regional economic considerations, study requirements/consent process. The costs associated with a beach drainage system are generally considerably lower than hard-engineered structures. They also compare very favorably with beach nourishment projects, particularly when long-term project economics are considered. Monitoring coastal zones. Coastal zone managers are faced with difficult and complex choices about how best to reduce property damage in the shorelines. One of the problems they face is error and uncertainty in the information available to them on the processes that cause erosion of beaches. Video-based monitoring lets collect data continuously at low cost and produce analyses of shoreline processes over a wide range of averaging intervals. Event warning systems, such as tsunami warnings and storm surge warnings, can be used to minimize the human impact of catastrophic events that cause coastal erosion. Storm surge warnings can also be used to determine when to close floodgates to reduce the physical impact of such events. Wireless sensor networks can be deployed quickly to set up a coastal erosion monitoring system, and scaled accordingly. Shoreline mapping. Defining the shoreline is a difficult task due to the dynamic nature of the coast and the intended application of the shoreline. Given this idea, the shoreline must therefore be considered in a temporal sense whereby the scale is dependent on the context of the investigation. The following definition of the coast and shoreline is most commonly employed for the purposes of shoreline mapping. The coast comprises the interface between land and sea, and the shoreline is represented by the margin between the two. Due to the dynamic nature of the shoreline, coastal investigators adopt the use of shoreline indicators to represent the true shoreline position. Shoreline indicator. The choice of shoreline indicator is a primary consideration in shoreline mapping. According to Letherman, it is important that indicators are easily identified in the field and on aerial photography. Shoreline indicators may be physical beach morphological features such as the berm crest, scarp edge, vegetation line, dune toe, dune crest and cliff, or the bluff crest and toe. Alternatively, non-morphological features may also be used. These indicators are based on water level, including the high water line, mean high water line, wet-dry boundary, and the physical water line. Figure 1 provides a sketch of the spatial relationship between many of the commonly used shoreline indicators. The high water line, defined as the wet-dry line, is the most commonly used shoreline indicator because it is visible in the field, and can be interpreted on both color and grayscale aerial photographs. The HWL represents the landward extent of the most recent high tide and is characterized by a change in sand color due to repeated, periodic inundation by high tides. The HWL is portrayed on aerial photographs by the most landward change in color or gray tone. Importance and application. The location of the shoreline and its changing position over time is of fundamental importance to coastal scientists, engineers and managers. Present-day shoreline monitoring campaigns provide information about historic shoreline location and movement, and about predictions of future change. More specifically, the position of the shoreline in the past, at present and where it is predicted to be in the future is useful for in the design of coastal protection, to calibrate and verify numerical models to assess sea level rise, map hazard zones and formulate policies to regulate coastal development. Accurate and consistent delineation of the shoreline is integral to all of these tasks. The location of the shoreline also provides information regarding shoreline reorientation adjacent to structures, beach width, volume and rates of historical change. Data sources. A variety of data sources are available for examining shoreline position. However, the availability of historical data is limited at many coastal sites, and so the choice of data source is largely limited to what is available for the site at a given time. Shoreline mapping techniques applied to data sources have moved towards automation in association with technological advances and the need to reduce uncertainty. Although these changes have resulted in improvement in coastal data processing and storage capabilities, the frequent change in technology has prevented the emergence of one standard method of shoreline mapping. This has occurred because each data source and associated method have their own unique capabilities and shortcomings. A number of the data sources used for shoreline mapping and their associated advantages and disadvantages are discussed below. Historical maps. In the event that a study requires the shoreline position to be mapped before the development of aerial photographs, or if the location has poor photograph coverage, it is necessary to employ historical maps in order to detail shoreline position. The main advantage and reason for using historical maps is that they are able to provide a historic record that is not available from other data sources. Many potential errors, however, are associated with historical coastal maps and charts. Such errors may be associated with scale, datum changes, distortions from uneven shrinkage, stretching, creases, tiers and folds, different surveying standards, different publication standards, and projection errors. The severity of these errors depends on the accuracy standards met by each map and the physical changes that have occurred since the publication of the map. The oldest reliable source of shoreline data in the United States dates back to the early to mid-19th century and is the U.S. Coast and Geodetic Survey National Ocean Service T-sheets. In the United Kingdom, many maps and charts were deemed to be inaccurate until around 1750. The founding of the Ordnance Survey in 1791 has since improved the accuracy of the mapping. Aerial photographs have been used since the 1920s to provide topographical information about an area. They are therefore a good database for compilation of historical shoreline change maps. Aerial photographs are the most commonly used data source in shoreline mapping because many coastal areas have extensive aerial photo coverage, therefore providing a valuable record of shoreline position. In general, aerial photographs provide good spatial coverage of the coast, however temporal coverage is very much site-specific depending on the flight path of the aeroplane. A second disadvantage associated with aerial photography is that the interpretation of the shoreline position is subjective given the dynamic nature of the coastal environment. This combined with various distortions inherent in aerial photographs can lead to significant error levels. The minimization of further errors is discussed below. Object space displacements, conditions outside of the camera can cause objects in an image to be displaced from their true ground position. Such conditions may include ground relief, camera tilt and atmospheric refraction. Relief displacement is prominent when photographing a variety of elevations. This situation causes objects above ground level to be displaced outward from the center of the photograph and objects below ground level to be displaced towards the center of the image. The severity of the displacement is affected negatively with decreases in flight altitude and as radial distance from the center of the photograph increases. This distortion can be minimized by photographing numerous swaths and creating a mosaic of the images. This technique will create a focus for the center of each photograph where distortion is minimized. It is important to note that this error is not common in shoreline mapping as the relief is fairly constant. It is however important to consider when mapping cliffs. Ideally aerial photographs are taken so the optical axis of the camera is perfectly perpendicular to the ground surface, thereby creating a vertical photograph. Unfortunately, this is not often the case and virtually all aerial photographs experience tilt whereby up to 3 degrees is not uncommon. In this situation the scale of the image will be larger on the upward side of the tilt axis and smaller on the downward side. Moore notes that many coastal researchers have not realized the severity of this error and therefore do not consider it in their methods. Radial lens distortion. Lens distortion varies as a function of radial distance from the isocenter of the photograph, meaning that the center of the image is relatively distortion-free, but as the angle of view increases the distortion becomes more prominent. This is a significant source of error in earlier aerial photography, but as technology has increased and camera lenses have become more refined, it has become less of an issue with later photographs. Such a distortion is impossible to correct for without knowing the make and model of the lens used to capture the image. However, if overlapping images have been acquired, one can digitize the center portions of the aerial photographs. Delineation of the shoreline. The dynamic nature of the coast has meant that accurate mapping of an instantaneous shoreline position has been associated with significant uncertainty. This uncertainty arises because at any given time the position of the shoreline is influenced by the short-term effect of the tide and a wide variety of long-term effects such as relative sea level rise and alongshore littoral sediment movement. Not only does this affect the accuracy of computed historic shoreline position but also any predicted future positions. As mentioned earlier, the HWL is most commonly used as a shoreline indicator. This can usually be seen as a significant tonal change on aerial photographs. There are however many errors associated with using the wet-dry line as a proxy for the HWL and shoreline. The errors of largest concern are the short-term migration of the wet-dry line, interpretation of the wet-dry line on the photograph and measurement of the interpreted line position. Systematic errors such as the migration of the wet-dry line may arise from tidal and seasonal changes. Storm-induced erosion is another factor which may cause the wet-dry line to migrate landward. Field investigations have shown that these changes can be minimized by using only summertime data. Furthermore, the error bar can be significantly reduced by using the longest record of reliable data to calculate erosion rates. Finally, it is important to note that errors may arise due to the difficulty of measuring a single line on a photograph. For example, where the pen line is 0.13 m thick, this translates to an error of a plus or minus 2.6 m on a 1/20,000 scale photograph. Beach profiling surveys. Beach profiling surveys are typically repeated at regular intervals along the coast in order to measure short-term variations in shoreline position and beach volume. Beach profiling is a very accurate source of information, however measurements are generally subject to the limitations of conventional surveying techniques. Shoreline data derived from beach profiling is often spatially and temporally limited due to the high cost associated with such a labor-intensive activity. Shorelines are generally derived by interpolating between a series of discrete beach profiles. It is important to note, however, that the distance between the profiles is usually quite large, and so the accuracy of the interpolating becomes compromised. In contrast to aerial photographs, survey data is limited to smaller lengths of shoreline, generally less than 10 kilometers. Beach profiling data is commonly available and from regional councils in New Zealand, such as those compiled by the Hawke's Bay Regional Council. 3. Remote sensing. Technological advancement over the last decade has led to the development of a range of airborne, satellite and land-based remote sensing techniques. Some of the remotely sensed data sources are listed below: multispectral and hyperspectral imaging, microwave sensors, global positioning system, airborne light detection and ranging technology. Remote sensing techniques are attractive as they are cost-effective, reduce manual error and remove the subjective approach of conventional field techniques. Remote sensing is a relatively new concept, and so extensive historical observations are unavailable. Given this idea, it is important that coastal morphology observations are quantified by coupling remotely sensed data with other sources of information detailing historic shoreline position from archived sources. Video analysis. Video analysis provides quantitative, cost-effective, continuous and long-term monitoring beaches. The advancement of coastal video systems over the past 15 years has resulted in the extraction of large amounts of geophysical data from images. Such data includes that about coastal morphology, surface currents and wave parameters. The main advantage of video analysis lies in the ability to reliably quantify these parameters with high resolution and coverage in both space and time. This in particular highlights their potential importance as an effective coastal monitoring system and an aid to coastal zone management. Interesting case studies have been carried out using video analysis. Turner et al. Used a video-based Argus coastal imaging system, to monitor and quantify the regional-scale coastal response to sand nourishment and construction of the world-first Gold Coast artificial reef in Australia. In addition, Smith et al. Demonstrated the added value of high-resolution video observations for making short-term predictions of near-shore hydrodynamic and morphological processes, at temporal scales of meters to kilometers and days to seasons. See also: coastal erosion, coastal geography, detention basin, ECO shape, integrated coastal zone management, coastal development, beach evolution, longshore transport, list of countries by length of coastline, Acropode, XBLOC, sand dunes stabilization, cuspate foreland, coastal sediment supply, Coastal Zone Management Act, references. Syria CUR, Rock Manual, the use of rock and hydraulic engineering. NWH Alsop, Breakwaters, Coastal Structures and Coastlines. Apierning-Addo, K., Ogden, M., and Mills, J. Pages 2008, A Euro Detection, Measurement and Prediction of Shoreline Recession in Accra, Ghana. Euro Unregistered Trademark Journal of Photogrammetry and Remote Sensing, 63, ppA 543 Euro 558. Anders, F.J., and Burns, Emma 1991, A Euro Accuracy of Shoreline Change Rates as Determined from Maps and Aerial Photographs. A Euro Unregistered Trademark, Shore and Beach, 59, 1, ppA 17 €26. Boak, E.H., and Turner, I. 2005, a Euro shoreline definition and detection, Arabia Euro unregistered trademark, Journal of Coastal Research, 21, 4, ppA 688 €703. Camfield, F.E., and Moran, A. 1996. A Euro defining and interpreting shoreline change, a Euro unregistered trademark, Ocean and Coastal Management, 32, 3, ppA 129 €151. Crowell, M., Letherman, S.P., and Buckley, M.K. 1991, a Euro historical shoreline change, error analysis and mapping occur, a Shire Euro unregistered trademark, Journal of Coastal Research, 7, 3, ppA 839 €852. Graham, D., Salt, M., and Bailey, J. 2003, a Euro National Ocean Service shoreline, a Euro past, present and future, a Euro unregistered trademark, Journal of Coastal Research, 38, ppA 14 €32. Letherman, S. pages 2003, a Euro shoreline change mapping and management along the U.S. East Coast, a Euro unregistered trademark, Journal of Coastal Research, 38, ppA 5 €13. Mayotte, S., Bhattacharya, A.K. 2009, a Euro shoreline change analysis and its application to prediction, a remote sensing and statistics-based approach, a Euro unregistered trademark, Marine Geology, 257, ppA 11 €23. Moore, J. 2000, a Euro shoreline mapping techniques, Journal of Coastal Research, a Euro unregistered trademark, 16, 1, ppA 111 €124. Morton, R.A. 1991, a Euro accurate shoreline mapping, past, present, and future. Proceedings of the Coastal Sediments, a Euro unregistered trademark, 91, pages 997 to 1010. Pajak, M.J. and Letherman, S. pages 2002, a Euro the high water line as shoreline indicator, a Euro unregistered trademark, Journal of Coastal Research, 18, 2, ppA 329 €337. Smith, M.W.J., Arninkoff, S.G.J., Weichberg, K.M., Gonzalez, M.M. Kingstong, K.S., Southgate, H.N., Roes Inc., B.G., Holman, R.A., Siegel, E., Davidson, M., and Medina, R. 2007, a Euro the role of video imagery in predicting daily to monthly coastal evolution, a Euro unregistered trademark, Coastal Engineering, 54, ppA 539 €553. Turner, I.L., Letherman, S.P. Beach dewatering as A Euro software, Euro unregistered trademark, engineering solution to coastal erosion, a history and critical review. Journal of Coastal Research, 13, 1050 to 1063. Turner, I.L., Arninkoff, S.G., Dronkers, T.D.T., and McGrath, J. 2004, a Euro CZM applications of Argus coastal imaging at the Gold Coast, Australia, Euro unregistered trademark, Journal of Coastal Research, 23, ppA 739 €752. Van Commonsveld, M., Davidson, M., Huntley, D., Medina, R., Arninkoff, S., Jimenez, J. A., Ritgul, J., and De Kruijff, A. 2007, a Euro A critical review of the Coast View project, recent and future developments in coastal management video systems. Coastal Engineering, 54, pages 567 to 576. Woodruff, C.D. 2002, Coasts. Form Process and Evolution, Cambridge University Press, Cambridge. External links, Delta Works Online, Coastal Defences in the Netherlands, Coastal Zone Management Policy and Politics class, Safe Coast Knowledge Exchange on Coastal Flooding and Climate Change in the North Sea Region, Ankara Coastal Wiki, Social and Economic Benefits of Coastal Resource Management from NOAA Socioeconomics Website Initiative, Coastal Resources Center, University of Rhode Island, videos. Free educational videos about coastal policy and zone management, The Future of Coastal Policy textbook overview, images, What is remote sensing? Unregistered trademark, image ND. Retrieved April 1, 2010 from http://www.amesremote.com NASA Long Beach JPG.